We will discuss the relationship between linear and angular variables. We know that acceleration changes in three respects. If the first is if the velocity magnitude changes. The second one is velocity direction changes. The third possibility is both magnitude and direction changes. Now, we will use these first two to derive some important relationships between linear and angular variables. The first relation is V is equals to R omega, and the second one is R A is equals to V square over R. How can we use this? Let's start. These are basically some useful relationships between angular and linear variables, which will convert the linear description of the particle into the angular description of the particle. So we start by considering a circle in which a particle is moving on the circular path, having radius r, subtended an angle theta. For example, the particle was firstly at position A, then it goes at position B, so it subtends angle theta, and the circle is of radius r. We say that, and with the velocity v, this distance is as s. We know from geometry that angle subtended is equals to arc length divided by r. This gives an important relationship S is equals to r theta. Now we consider that this particle rotates in a very small interval, let's say dt. So what would be the velocity? Velocity is simply is equals to the distance covered per unit time. Since we are considering very small distance, so the a very small time interval, so the distance covered in that time interval will be converted from s to ds. As a theta, also theta would be converted into d theta. So the angle subtended also becomes d theta from theta. As we know that theta is equals to s over r, so d theta is equals to ds over r, where ds is linear displacement and d theta is angular displacement. Okay, angular displacement means angle subtended by the arc. Okay, now we are dividing it with del t dt. Since a particle is moving in a very small interval time t dt, we are considering the time t dt. So it becomes d theta divided by dt is equals to ds divided by dt divided by r. Means what is this? This gives us rate of change of angular angle in unit time. Rate of change of angle in unit time, also called as omega. which is angular velocity, means angle rotated by radius r in unit time dt. Angle rotated by radius r in unit time dt. So it has the units since omega is equals to d theta by dt. So it has the units where angle is in radians. So it will be radian per second, its unit in SI units. Now, d theta by dt is omega. So here comes omega equals to ds by dt is equal to simply v because it is linear displacement. Linear displacement means distance covered per unit time in a linear motion divided by r. So v is equals to r omega. This is a relationship, first relationship which we were going to derive. This is the first relationship. Some important formulas from this relationship is omega is equals to d theta by dt. If this theta is of one complete revolution, so this would become 2 pi radian divided by capital time t. So omega average is equals to 2 pi divided by t is an important formula which is used in different examinations. Now we are going to derive another important relationship which says A is equals to V square over R. Also, before that, we will also discuss another relationship which is A is equals to R alpha. Basically, the net acceleration has two components. The first is tangential component and the other is radial component. Tangential component and radial component of acceleration. The tangential component of acceleration depends on the magnitude of velocity. Magnitude of velocity means here we will see that the speed changes. For example, if the particle is moving in the circular motion, then the speed changes. If the speed changes, the particle will complete the revolution in earlier time, and if the speed lows, it will complete this rotation in later times. It will take more time. But when it is going with uniform speed, it gives the radial acceleration. Uniform speed, it gives radial acceleration. In radial acceleration, the speed is constant. Speed is constant. Only the direction of velocity changes, which gives us radial acceleration. What we have to keep in mind is that tangential acceleration is gained from the change in speed, where the magnitude of velocity changes, and radial component of acceleration is gained from the direction of change in the direction of velocity. And how these are derived? Let's start. So, we are considering again the circle in which the particle is moving on the circular path with a velocity v in a small time interval dt, separating an angle d theta of radius r in this very small distance it traverses ds. As just now, we derived the relation v is equals to r omega. If we divide, if we consider very small interval, so small displacement and very small amount of velocity. So it would become dv divided by dt is equals to r d omega divided by dt. Focus here that the velocity is changing. Since the linear velocity is changing means the speed is changing, so that we would divide dt with d omega with omega, because as we discussed earlier that linear velocity is linked with angular velocity. If this changes, then ultimately this will change. If this remains constant, then ultimately this will be constant, as we will see in the next relationship. Here, when the velocity is changing in magnitude, it means that this is change in speed. Remember that this is change in speed with respect to time, which gives us tangential acceleration, as we discussed earlier. One part of acceleration only, which is tangential, are same as it is, and we know that d omega by dt is equals to alpha, which is the angular acceleration. This is alpha. So, tangential acceleration is the acceleration which has come from the force, which is the force along motion to increase the speed. Force along motion to increase, again, since this is the change in speed, increase speed gives this acceleration. For example, the particle is moving in circular motion. The force required to increase in its speed is along its tangent. So this is a tangential acceleration, whereas this is the component of acceleration along the motion. Component of acceleration along the motion. So AT is equals to R alpha. Now we are going to derive the important relationship of another component of acceleration, which is radial component, which is equals to v square over r. As for this, we can simply say that F is equals to mv square over r, which is centripetal force. Centripetal force. And we also know that F is equals to ma from the Newton's third law. If we compare these two equations, it would become mv square over r is equals to ma. So we can simply have A is equal to v square of r. But how we can derive this from considering the velocity? As for tangential component, we said that the speed is changing. For the derivation of radial component, we assume that speed is uniform or constant. So when the magnitude or speed is not changing, but the acceleration is not constant, this implies that there must be a change in direction of velocity, which would give us the radial component of acceleration. So for this, again consider the circle in which the particle is moving in the circular direction. Let's suppose the particle first have velocity v1. Since the direction of velocity changes, so here the particle is moving with velocity v2. Remember that v1 in magnitude is equals to v2 in magnitude. Let's say this is v. Since speed is uniform where this is angle theta and this is r radius. Now, if we consider this triangle, let me draw separately. It would be somewhat like this. These are the radial parts, and let's say this is distance s, and this is the angle subtended theta. The other triangle, if if I draw this v1 and add the other velocity component by head to tail rule, it would give me these two components. And I'm drawing a unit vector here for the completion of head to tail rule. Let me draw this little bigger. This is v1 by head to tail rule. This is v2, and this is the resultant vector v1, v2. This is del v. So by geometry, we also know that if this line, let me use another color, if this line is perpendicular to some line and the other line is perpendicular to some other line, then the angle between these two lines is same as the angle between those perpendicular two lines. This is the rule gained from geometry. So this theta and this theta would be same. Also from head to tail rule, we can see v1 plus v2 since the arrow is at the head, arrow is at the tail of del v. So by addition v1 plus del v is equal to v2. This implies del v is equal to v2 minus v1. If we consider very small displacement, so the s would change from s to ds and theta would change from d and theta to dt theta, and velocity v would change from v to dv. Also, since the triangles both this and this are isosceles, so their congruent sides would be equal. This implies that if we consider ds from this triangle, s is changing to ds by considering very small time interval dt divided by r, which must be equal to, in this triangle, what is ds? If this is s is changed to ds, then the v is changed to, since this here del v is equals to v2 minus v1, it must be equal to dv, since considering very small interval dt. So dv divided by v1 or v2 or v, it's simply same because the speed doesn't change. Now dividing by time dt, where small time interval dt, ds divided by r dt is equals to dv divided by v dt. Now, simply this would give us the velocity, since the change in displacement distance divided by time is velocity divided by r is equals to. And dv by dt is simply nothing but the acceleration. This implies acceleration is equal to v squared over r. This is the radial component of the acceleration, or we can say net acceleration, in which the velocity direction changes only, not the speed or the magnitude. The second method for this derivation, a is equals to v squared over r, is a bit easy. As per considering tangential component of the acceleration 0, we can say v is equals to r omega. If we divide dv by dt is equals to omega dr divided by dt. Remember, in the derivation of at, we divided omega with dt because the v was changing. If the v is changing means linear displacement, the angular displacement, that is velocity, must changes. But in this case, we assumed previously that linear acceleration, a linear displacement, and angular displacement is constant. So these both doesn't change. This dv by dt would simply give the constant acceleration or the net acceleration, whereas omega, and this would give us dr by dt is simply velocity, change in displacement with respect to time. Now we know that v is equals to r omega. From here, omega is equals to v over r. So by putting the value of omega v over r into v is equals to v squared over r. And this completes the proof.